All right, tonight's speaker is Scott Ewart. Scott grew up in Philadelphia area and developed a keen interest in astronomy about the time of the comet Hale-Bopp came around. That's when he bought his first telescope. It wasn't a very good telescope, and upon investigating why, he discovered his talent, at the very least, for telescope rehabilitation. And in other words, fixing up telescopes to perform better. Um, that began Scott's journey into telescope making. In 2005, Scott moved to New York to take a position at Tele Vue making telescopes, of course. And he now works in quality control and an electronics company and recently caught the telescope making bug anew after a few years of just using them. And his telescope making adventure continues. Scott's presentation tonight is titled My Adventures in Telescope Making. And he will cover his personal history of telescope making, but mostly cover the construction of his latest telescope, his split ring equatorial Newtonian. With that, let's give a warm welcome to Scott Ewart.
Um, so that's the telescope I have now. It's what I built. This has been 20 years now. 2005 is when I finished that. And where it started was this little guy. And this started out as a Chinese mail order Tasco. It wasn't very good. It was a spherical primary, which at f4.5 was ridiculous. It had some design features that kind of masked it a little bit, so you were kind of not that badly viewing the spherical operation. But yeah, I figured out that if you try to fix the masking, then you see more of the aberration. Yeah, so found a guy out in Colorado, refigured the mirror, changed the tube, and just kind of rebuilt everything, and now it works quite well. And after a couple years using that, I went to the Texas Star Party in 1999. That was my first big star party, and everybody had big telescopes, and of course I caught aperture fever, and this is the scope I bought, and that also needed a lot of work. It worked okay, but I didn't like how the eyepiece stuck out the side, straight out the side. It started out straight here, and I rotated the whole tube so the eyepiece is up here. So when you're viewing low, you don't have to sit on the ground. So yeah, that and many other mechanical modifications. I added the finder scopes and changed the mirror cell. Eventually, it had a very thin mirror. It didn't perform very well, so I changed that and got a mirror. The next mirror performed pretty well, but I eventually refigured it after I built my other scope, and now Willie has that. Now I guess the rest of the scope is you sold the scope and basically you just used the mirror.
Every part of that scope got used by somebody.
Okay, that's good. Yeah. All right. Good. Good.
I got the mirror, and Rob Teeter built the whole.
Right. Right. Yeah. Okay. So then, while I had this, I wasn't in any hurry, so I wanted to scope that tracked the sky. So that's when I started building the split ring. But in the meantime, I bought a smaller, more portable scope that's easier to plunk down at home, and I've had that for probably just about as long. I bought that actually. Then I got this mirror from a friend of mine, Bernie Kosher, who helped me with the new scope I was building. But he had parts of this, and I built the base and some other parts. He built this Crayford focuser, a homemade Crayford focuser. I built I think the center section here and the base, but the mirror was superb. think he sold it to me, but didn't pay much for it. But this performs incredibly well. It's just it's not much to look at, but it works really, really well. And then when I started working at Tele Vue, started building telescopes, this telescope is an NP101. Now, there are plenty of Tele Vue NP101s. I built some of them, and there are plenty of brass Tele Vue scopes, but there are no other brass Tele Vue 101 NP101 scopes. This is the only one in existence. I had to custom make the tube. I cut it and rethreaded it and built an obsolete focuser out of rejected parts. And so this is another scope that I use occasionally. It's very easy to just walk it outside, plunk it down anywhere, and start observing. It's a very good scope for planets, anything.
How big is it?
It's a 4-inch.
Okay, thanks.
Yeah, and it has a very wide field. And actually, there was a particular object called Hewitt 1. It's a very large, like a 2-degree planetary nebula in the constellation Sextans, and I wanted to see it. It had just been discovered in 2006 or something, and I needed a really large field for that. And despite the fact that it's small, if you get to a really dark site, it's a very, very faint planetary, very hard to see, but several other people saw it. And so I accomplished my mission. So yeah, it's a very versatile scope. So in the meantime, I had started building this. About 2001, I bought the blank. Right here, I had already done a lot of polishing on the other side. This is the back side. And as you can see here in these areas here, it's where it wasn't flat. The mirror was, it's called black vitrified ceramic. It's made out of a bunch of layers of ordinary soda lime glass, but it's not ordinary, it's a special glass, but it's baked and turns black, and you get air bubbles between the layers, and that causes ripples in the back because it's cast face down. And so I was well into polishing it and got astigmatism. And I thought, well, as a precaution, in case it's the support from the back, I'll regrind it. So that's what I did. All this time, I had a lot of support and guidance from my mentor, Bernie Kosher. This is his basement, and I'm grinding the back of the mirror here with a flat piece of glass. Yeah, he was very valuable to me. I'm living in Philly and driving to Trenton to his house, and he got me going, and he was wonderful. So it helps to have a mentor. So this is what a mirror and grinding tool look like. This is my current 8-inch. I'm building this now. It's meant to be used as a finder for my large scope. The channels are ground in there with a diamond wheel on a grinder. And the reason they're there is because when you get down to a very fine powdery grit, if the mirror and tool stop moving, you have a problem. Because when you have water in between there and just a few microns of space, that you need you need to get some air in there in order to separate them. So that helps. The channels help allow you to get some air. You can have a real problem getting them apart. So that's why, and it gives the slurry a chance to move around, and the ground up glass a way to get out. So that's what those channels are for. And you grind the one on top is the mirror, and that when it's on top, you have this overhang here, and gravity tends to grind more in the center. And because you have, this is overhang and not get ground. And then on the tool, you're grinding the gravity of the tool of the mirror grinds more around the edge. Now you do strokes back and forth all across it, and random, you rotate the mirror, you rotate the tool the other way, and so everything's randomized, and you end up with a spherical surface, and one's concave, the other's convex. So that's how that process works. And when you get to where the depth you're looking for, you use a spherometer. It's just a disc of aluminum. I got 3 different ones here. This is for small lenses. This is for a medium-sized lens or mirror, and this is 6-inch for this. The bigger you can make it, the more accurate it is. But you're just measuring. You zero this on a flat. I have an optical flat. It's flat to within, I don't know, a few nanometers. So you get your 0 point, then you set it on here, and whatever this dial reads, that's your depth. And then there's a pretty complicated formula for figuring out the radius of curvature based on that depth, and you get you have to know exactly the distance between the balls, and you plug that all into the formula, and the diameter of the balls too. These are ruby. Most people use stainless steel, but ruby is better. It doesn't wear. You would think stainless steel doesn't wear, but you drag it across ground glass, you get a flat spot on your on your ball bearing, and it's useless. So I got ruby balls, and works better now. And the ruby is actually less likely to scratch the glass. A harder. Hmm? Yeah. This disc was already made for me, but I made these other 2 discs, and you just put set screws in there, and it grabs the indicator. And yeah, again, there's a Excel file, a simple spreadsheet that you just plug the numbers in, the diameter, the measurements here, and that's it. You just tell it how deep it is, and it'll tell you your radius of curvature. And this is a pitch lap. Once you've ground the shape you want, you have to polish, and this is pitch. It's rosin and tar. I forget, but it's a very viscous liquid. It seems solid, but it'll chip if it's cold enough. But it flows. It flows very slowly, and makes it conforms to the shape of the glass, and makes it the polishing compound actually embeds into the surface, and that scrapes the glass, and on a microscopic scale, and makes it shiny.
What are we looking at there? Is that a fabric or?
Oh no, that's the I don't know what gives you the texture. The channels are there again for so that the pitch can flow better, and you don't get, and it doesn't stick. But the surface itself, it might have, I'm not sure, but it's actually probably a 1/4 inch deep. What you're seeing, those channels, and then the surface here is just whatever it was stuck down on, but it picks up the whatever texture it had. And once you've started polishing, you need to know what the shape is, and to test that, you need a Foucault tester. And this is very much like what you see on the design on Stellophane's website. They have plans for building it. It has some features that that I thought could be improved upon, so I needed to build one. When I first built my other mirror 20 years ago, I just borrowed a tester, so I didn't have a tester to make my new mirrors. So I had to make a tester, and so I looked at a whole bunch of images online, people's ideas, and I came up with some that I really that I think really help improve the design. first of all, when you're trying to look through this, right, you put your eye right behind the razor blade and get it as close as you can. That gives you better definition of the surface you're looking at, but there's no room for your nose. So this is all open, and you just put your eye up here, your nose goes here or here, whichever side you want to look through, and everything else is, And the other thing I added was that I saw one online, a picture of, this is variable elevation. You could raise and lower this. And it's much easier when you have a mirror 20 feet away, and you have to adjust the level so it's pointing directly at this spot right here. The reflection of this LED is pointing right here, and rather than walking back and forth across that 20 feet to adjust the tilt of the mirror, you just move the whole thing up and down, and it's just saves a lot of time. So I'm almost done this. It's I had to I changed the location of this because it wasn't balancing right. This, when you move this up and down, it moves the knife edge left to right. And that's important to get it exactly where you want it. This adjusts the fore and aft motion. That gives you the measurements you need. And this takes the measurements. And this is what you see, sort of. This explains the concept of how it works. The knife edge cuts across the return beam, and like if the knife edge is inside of focus, this is what you see, and if it's outside, this is what you see. And if it's right at focus, it grays out all at once as the knife edge is cutting across. Let's see. This is what you see in reality. This is probably a very good mirror. This is not my picture. It's just a picture I found online. But this is basically what you see when you're looking through a Foucault tester. This shows the areas that are, this is inside focus, this is at focus, and this is outside of focus. And you need to have, for a parabolic mirror at the radius of curvature, the focus point is different for every point from center to edge. So, so this is how you measure it. You find where the ring is uniformly gray here, and you take the measurement from where that's gray to where it was gray in the center or gray at the edge, and so that's what you're looking for in this test. Now, this is an example of a mirror with a problem. The problem is it has astigmatism. You can see that in the fact that you have light here and it's dark here. It's kind of a yin-yang pattern. You got the light here, and then you got the dark here. It should be uniform, straight up and down like this. And when it's twisted, you got a problem. You have part of your mirror focusing closer than in one axis than it is in the other. And you got to fix that, and it can be a pain. This is what you see when you look through a Ronchi grating. That's basically lines of just light and dark, and it can be ink on a transparency, or you can make it yourself with wire. The mirror on the right, or the image on the right, is probably a fairly decent mirror. Now that it has a turned edge, you can see the shadow gives a little hook right here. So that should be fixed, or you'd have to mask it off. Some people do that. They can't get rid of it, and it's just a 1/4 inch, just forget it, just lose it, just paint over it. So this one looks like it has a hole in, no, it has a hill in the center. And it also has a turned edge. So this is an example of what you're looking for when you're looking through a tester, and you have these problems, you have to fix it. And this is what I made. This is a Ronchi grating, homemade. And the way you do this is you put the backs together like the blue. This is just an ordinary slide frame from 20 years ago when they used film, and you you take two halves and you clamp them back to back, and then you take two strands of wire and wrap them very carefully and very tightly around both frames, and you glue everything in place. And then you unwind one of the strands so it leaves a gap between one strand and the next. And then you still have two that are wrapped together. You grind off the edges so that you're basically cutting them free. And then you put more glue on and you slap on the other half. And now you have two of them. You kind of have to make two. You throw one out if you want, but and I'm not sure yet if they're uniform enough. I'll know soon if they, but this is just yeah, it's the wires. It's like two lines per millimeter or something, two wires per millimeter, I think, something like that. And this is what a really good mirror looks like through the Rocky test. This is outside focus. The focus is closer to the edge than the center. So anyway, you're looking for a very gradual progression of the curve of these lines. It should be pretty straight in the center, and then gradually hook more and more, and right at the edge you get a pretty quick turn. And this doesn't quantify what your mirror is going to look like, but it gives you an idea that if you have a zone, you'll see it'll get a straight section here and then a sudden bend. That's not good, because then you have two areas close to each other of the mirror that are pointing in different directions. So this kind of gives you an overview of everything all at once. Basically just the quality of the mirror, not the quantity of the numbers for that. Oh, here's another. Yeah, okay. So this is a mask that you use to actually take the measurements. This one is focused on this area. They're both evenly gray here and here and here. This is a very good mirror. This is not a good mirror. It has surface roughness, and it has a zone right here. It's kind of a sharp transition between the edge and inside that. So that's something you need to look for. So you get your measurements, okay? You take your measurements here, you see how much distance you move the knife edge from one zone to the next. Okay, now you have a bunch of numbers. What do you do with them? You write them down. This is an interesting slide here because this has a lot of information on it. I made these printouts, and every time I did a spell of polishing and figuring, I took a set of readings. And so there's 4 per page. This is page 25. That's 100 readings. And that's just when I started using this system. That doesn't even start at the very beginning. It has the dates, 217, 225, another one, 225, and 226. It helps to take notes. So this is, I'm using a 10-inch tool. I had different tools that I was using. The 10-inch diameter tool, I was using a smaller one, a couple smaller ones, and I think a 6-inch, even smaller one. But I would take notes, 10-inch tool. 4 inches over. So yeah, the 10-inch tool is long strokes because of 4-inch overhang. Pressure over the 5-inch zone. In other words, 5 inches from the center to the edge. And it's a quarter wave overcorrected. So I'm sorry, 16th wave overcorrected. And so when I go to do the next one, I know what I did last time. It gives me something to refer back to. This is interesting here. It's even better. It's 20th wave, but I wasn't done because I looked at other things that told me that I can do better. And it should be a very, very good mirror. But I guess, what did I say? The edge is a little flat. So, okay. It's still 20th wave, but it could be better. I went at it again. Now it's 10th wave. It's undercorrected. But the very last one, I made notes of what I did, but now I'm getting close. So I got to take 3 readings and average them because I don't want to make any mistakes. I want to make sure that it's what I think it is. And these numbers don't mean a whole lot. You want to get them close to the ideal numbers, but there's freeware that helps you crunch the numbers. This was called Figure 45. It's an old DOS program. It's now available as Figure XP. It's freeware. This is pretty straightforward to use. You plug in your readings. You enter your parameters first. You plug in your readings, and these are the various readouts you get. This shows the surface error. So this is right down at under 10 nanometers of surface error, which, when you think about it, it's pretty cool that you can do this by hand. But yeah, and so it gives you all these encircled energy, Strail. They're about the same. I forget what the difference is. This shows that there's still a quarter of a cubic millimeter of glass that you could remove to make it perfect. Even though it's only 10 nanometers of error or less, that's, so now it's 1/28th wave. And the transverse error is that is defined as the distance from the center of the airy disk to the edge. In other words, a transverse error of 1 is a zone that points to the edge of the airy disk. And this represents the airy disk, the thickness here. So the edge is still pointing close to the edge. Even though it's 28th wave, it took this long to get that under 1. And so that's why I stopped. And also because I looked at it and I'm like, well, what stroke do I use? Where do I take glass off now? And I couldn't come up with an answer, so I was done. Basically the perfect mirror was there all the time. I just had to scrape off everything that wasn't the perfect mirror. Now this is a kind of a visualization of what the airy disk would look like, the energy. This is the airy disk to the radius. Then this is the first diffraction ring, second, third, and the departure from perfect. Now this is unobstructed. You add an obstruction and you change that into this actual depiction. And that's what you have. And my obstruction is fairly small, it's 17%, but that little obstruction has its own diffraction pattern, and that gets superimposed mathematically on the other one, and this is what you get. And it gives you a different way of looking at it. This is without the obstruction, that's with the obstruction and the surface error. So it gives you an idea of what a bright star would look like on a pretty good night of seeing. So mirror's done. Meanwhile, I'm working on the rest of the scope. There's a lot here. There are 6 truss tubes. This one without the shrink wrap is stainless steel. So I have something to run the sliding counterweight on. That's very useful if you're using a shroud. You can have the shroud up. If it's windy, you pull it down and you raise the counterweight to compensate. Let me zoom in here. So this is the mirror cell. I bought this part, the 2 main slabs, it's cellophane. It had a lot of holes. I drilled some more holes in it and enlarged some holes. So It's a little lighter. It's still kind of heavy, but it's heavier than it needs to be, but it's very stiff. And I actually used a milling machine to cut the thickness down a little bit too. There's freeware to design the flotation cell. This is a 9-point cell that floats on these 3 points, and it will give you the measurements of where the center of the support points go, and it optimizes it, gives you the least flexure of glass. You tell it how thick your glass is, what kind of glass, and how big your central obstruction is, all that stuff, and it'll tell you everything you need to know to make a 9-point support, or a 6-point, or 18-point, or whatever you want to do. So this, I bought this before I finished the mirror, and I didn't have something to put it in. And I see this keg in my neighbor's garage, and I'm like, wait a minute, how big is that? Let me measure that. And it turns out that the diameter of this, the cell that I bought, is almost exactly the diameter of the lip of the keg. It's actually in the bottom lip, but this is it worked out very well. And so I needed something round so I could rotate the tube. The only other alternative for an equatorial scope is you rotate the upper cage. So that has to have a very precise alignment, has to be very smooth. But oh, I guess I can. Oh yeah, okay. So yeah. Anyway, so I got this keg and I started cutting it, and I wanted it lighter, so I got a hole saw, and that's very hard to cut through stainless steel with a hole saw. But anyway, I installed a fan to blow across the face, and I wanted insulation also. As you can see, the insulation here, there's a layer of plastic in here, and the insulation to keep, because I didn't know how the metal would affect, having metal close to the air, to the optical path, and if there would be heat waves coming off it or whatever. I wanted to make sure it wasn't exposed. So and the other thing about this is it shows that the difficulty in constructing the way to rotate it. It has these 2 stainless steel rings, one here and one that's already mounted, that gets mounted on here, 12 mount points, and then you have 6 bearing points on both sides. Everything's adjustable, and you have to tweak the adjustments so that you eliminate all the high spots and low spots of the ring, and any gaps between the pads and the ring, and they're set at 45-degree angle. These are Teflon buttons set into Delrin. It's all this is all just stuff that I had to make to get it all to work. This is a stainless steel pipe, 18-inch section of stainless steel pipe. It was 20 pounds. I wanted it lighter, so I drilled more holes. Then it was too flexible. It went from 20 pounds to 10 pounds, but it was too flexible. So I added this fiberglass. So these are some ribs of fiberglass I folded over, and it's a very thin strips of fiberglass fabric, and it's like 20 layers altogether. It's only, I don't know, a 1/4 inch thick or so, but it went from 10 pounds to 14 pounds, and it ended up much stiffer than it was even before I started drilling the holes. So that worked out really well. It was a little work, but anyway, it was worth it. So so that's support. This is the declination axis here, and so it swings from these bearings, and then you rotate the keg within it so you can position the eyepiece where you want it. So I guess we can move on to the next one. Oops. Why am I gotta get out. I got to back out. Yeah. Okay. Yeah, I bought this in the process, somewhere in the middle of building the scope. I bought this. I had a lot of help. So before I bought this, there was, the guy that lived next door, the guy that I got the keg from his basement. He was a machinist. So I got these, like they were torch cut stainless steel rings, and he made these nice, he uses CNC to cut the nice 45-degree angle on it, and so all it cost me was cutting his lawn, and so yeah, it worked out pretty well. So he helped me out a lot, and yeah, and so this helps a lot to have this in your arsenal. Yeah, it's really nice to have. Now the split ring. This has an interesting story to it. It's kind of isolated here. You can see how it all went together. It's got, bracing to keep it from flexing in that axis, and then bracing across here, the supports from here, but this keeps it, the ring fairly well supported, but yeah, there's a weak spot in here because it's unsupported here except by the other end. But the span is from here to here. That this distance can't change much, only the flex of that stainless steel tube you saw. But when I was welding it, you have to weld the ends of the square bar to the round bar, and so you weld along the sides, which is where I should have stopped. And for cosmetics, I welded around the end of the square bar. That was a mistake. What happens when you weld something like that? Weld is very hot. It's molten. So as it cools, it contracts. And when I finished welding the two square bars to the round bar, and I had to have the round bar, went to a fabricator and had it rolled. It just goes between 3 rollers and gradually bends it as you squeeze the rollers in. Anyway, so it was nice and perfectly round. But then when I was done welding, these 2 points here and here were a full inch too close. They had moved 1 inch. I almost had to abandon this and start over. So again, my neighbor with the milling machine, I gave him a little sheet of steel, of aluminum, and I said, cut me a radius of 16.25 inches into this. And so that's what I used to straighten it. Just that and a lot of brute force. I used this as a template, so I laid it against here and just kind of banged it against a carpeted floor and pried on it until I got it right. And it's pretty close. It was a hell of a recovery, but so anyway, yeah. So now it's all welded together. How do you have to have a south axis that it pivots on? So where do you put that? How do you know where the center is exactly, the center of rotation? Well, I built this jig with just some pieces of wood I had laying around. So the ring is touching here, here, and here, and you rotate it within those confines, and you stick. This is a nail stuck into the wood, and I bent the nail until the head of the nail was exactly over the 1 point on here that doesn't move as you rotate it. And so I marked that and put drilled a mark in it then, and then I welded the axle onto it. But yeah, it took me a while to figure out, let's see, how do you find that spot? And yeah, it's very important to find that spot. All right, so this shows this is a toy car battery, 9.6 volt, and this powers both the fans. There's one here and in the middle of the cell underneath. And then it also powers, and this is the two switches for the fan, but it also powers the dew heaters for the top, for the cage. And as you can see, all the wires are hidden. This is the charging port for this, so you don't have to dig this out of its pocket in here. You just plug the charger in here. But all the wires are hidden in there. Oh, back one. Right here, you can see where the truss tubes mount. These are just a piece of plywood with a slit across. So how do you know exactly what angle to drill these holes? If you're going to grip it with just a tiny bit of displacement here, it has to be precise. So how do you know what angle? Well, this was early 2000s. Got a friend had a free version of AutoCAD Lite, and I learned how to do a 3D rendering in AutoCAD. So I put the rings, the top and bottom ring that the tubes would mount to at the appropriate distance, and drew in the tubes, and asked it, what are these angles? And so this is one view looking from the top down. I drew in two of the tubes because I wanted to see the upper bolt circle is a little bit smaller than the bottom one. So I wanted to see in the middle, the center of the tube is actually closer to the center of the mirror than in the ends, because it's kind of cutting across. So it's easier to see in another rendering. But anyway, this is the top, and you can see that the angle, like measure between the two holes, then you have a tangent there, and then you need to know not only the angle down to the other ring, but you have to know the angle of departure from that tangent. They're not pointed straight out. They have to point towards the bottom of the where the other end goes. So you draw this line, and so you have 25 degrees of difference here and 82 degrees of angle there. And my friend with the milling machine, at the time I didn't have one, he had the adjustments to drill the holes exactly where he needed them. And of course the bottom is different because it's a larger bolt circle, so you had to reach in to the center more, 35 degrees in this case. 82 degrees is still the same. But and so this is exactly top down, and this shows how one tube from starting out here cuts across into to a smaller diameter to reach down to the point below. And I wanted to make sure that it didn't interfere with the light path. And so this is what it actually looks like in practice. You can see the tube going from the top down to here, or the top down to here, and it is visible. It cuts across, but the edge of the mirror is here, so it's not a factor. But you do have to have strings in between the tubes to keep the shroud from going straight across here or straight across here, and that really would cut into the light path. Next. Okay, so in the upper cage, this is how you mount a finder on just a ring of aluminum. You just screw a block to it and then put the dovetail here. This shows the wire that goes to the heaters. I have a heater that's actually nichrome wire from an old soldering iron that's wrapped directly around the glass, and there's a connector here that you can plug in and unplug. The only way to focus is to unplug that and twist the cell. It's threaded, and then this is the lock ring. So it had to be an unpluggable connection. And then there's also wire wrapped around the bottom too. But when you do the heat directly to the glass, you need very, very little wattage. like maybe a 1/4 watt total for this finder. And that keeps the dew off if you need it. Let's see, here's, you can see from the other side, here's the connector there and the wire going down to where it plugs in, and then there's another wire down to here. And this also shows the finder on top of a finder, hold another little mount onto the other mount. So you've got a red dot and an optical finder. I find them very useful to have both. All right, and let's see. Yeah, it covers that. All right, and this is a 2" to 1.25" adapter, but this is a very fine focus adapter. So, I forget, it's maybe 16 threads per inch or something. So you turn this, several degrees and you can barely see a change in focus, but yeah, it matters when you want the finest focus. And this is like a special grease I used at Tele Vue, and so it doesn't wobble around. You have to cut the threads very, very carefully, but yeah, there's no wobble or anything. It's kind of a very smooth feel, but and I like making them out of brass because you make it heavy so that the balance of the scope, it doesn't shift when you put a heavy 2" eyepiece in. You already had the weight in there for the 1.25", and you take that out and you put the heavy eyepiece in, and it's about the same. This shows these are the switches for the dew heaters. The wires hit in the truss tube. That's, everybody does that. But these wires come out the back of the focuser board and they go into the ring. So here is the inside edge of the ring. I've dremeled a channel into the ring to go from the top of the truss tube where it plugs in right here and then that connects over to here, and this connects to the finder. So you got the power to the finder, and then you got the power to, this goes up inside this tube, and this goes out to the secondary. So you have a heater on the secondary, and this is the switches for it. So to wire it all together, this is a very fine 30-gauge wire. So you slide it all in there, and nobody sees anything. So yeah, I went to great lengths. I had a lot of time. And this is what you do with the wire to hide that, not only from view from, cosmetic, but you don't want to add to the thickness of the spider vane because that adds diffraction. So you glue it to the very edge of the vane, so it doesn't add to the thickness. And so that goes into here. There are 3 resistors, again, glued directly to the glass. Actually, I think I used CPU glue. So the glue itself conducts heat. So you get very, very efficient heat transfer. And again, it takes very little power. And that little battery doesn't have a whole lot of capacity, but it'll last for a couple nights. And of course, what good is a keg without a tap? I thought, I just had a regular knob on there for a while, and I thought, yeah, I should get one, So I found this on eBay or something, and it's like, yeah, that's perfect. So that's an actual wine cask tap or whatever it is. Yeah, and I thought about, like a bar tap handle, but that'd be too big and that would get in the way. So yeah. All right, the base. This thing took me 2 weeks to make, and a lot of time with the belt sander, getting the shape just right, getting the angles right, getting it all to fit together. It's all screwed and glued, and yeah, and it's the thing is, there's no drawing for this. I built it for 38 degree latitudes, and so the screws or give you, you know, like a 8-degree adjustment. You know, you can add 8 degrees for, you know, for to go north, you crank these up, and to go south, you crank this one up, and it'll take you down to 30 degrees, which is good for Texas and North Florida. If you want to go to the Winter Star Party, you got to put a block under here to get it up even higher. But this is how you adjust it just for latitude. I have an angle finder that I slap onto the ring to show the angle. One side note here, I said that the axle for that goes into the south and into the ring, you know, from the ring, has to be exactly centered. Well, it's close, but you can see by the wear on here on the drive wheel that it's not. That should be a perfectly straight, thin line, and it's like a 1/4 inch wide, so that it does walk a little bit, but it's pretty close. It does have the effect of when it walks, it changes the tension on the clutch a little bit. Every little thing, you gotta, you gotta watch every little thing. Yeah, so this took a while to build, but it's very, very rigid. It's surprising how, you know, and it shows the counterweights you can screw onto the back, and they clear the ring. If you want to add like a bino view or something really heavy to the top, you have to add the counterweight to the bottom. But overall, everything's pretty well balanced. For a split ring, you have to balance everything in every axis. In other words, the focuser is on one side, so you have to balance that with weight on the other side. Like if the focuser is up on above this area here, then you put a little bit of weight into the lip. I melted some lead into the lip of the ring, the keg rather, and there's a little bit of lead melted into the ends of the split ring because you have the missing mass of the ring that's not complete. And to get everything as compact as possible, you have to have really tight clearances. And this shows that I even had to grind off the edge of this flathead screw to make sure it wouldn't catch on here. There's 6 of these, and yeah, before I did that, every once in a while you get it a little thump. And it's, you know, the planning is, you have to be very careful how you plan. It's the clearance, you know, this is a 4D battery pack. You have to notch the wood to make room for it so that this corner wouldn't get hit by the ring, the south extension coming by. Here's a clearance issue where this is the clamp block at the top of the keg, and as you rotate, that has to clear the declination axis. So you have just enough room to clear the attaching nut, but then you have to make sure that the knob clears. It's just it's a lot of planning. All right, so to control the motion of the axes, you have to have in this case, I opted for a tangent arm. And so I saw this picture and I thought, yeah, that's a good idea, because I tried other methods of attaching, but this is what allows you to move. Well, it's easier if I show. Yes. So the screw that adjusts the motorized screw that adjusts the declination is a line, and obviously the end of this swings through an arc. So you can't have a rigid connection, just like have the screw go right through a nut or a threaded passage. It doesn't work. It has to float. And so this is the design kind of, you have to have the hole for the screw to go through and a hole for the, this is the threaded piece. And then it has to float in this axis also. And this is what it looks like. The motor driving, there's a gear in here, there's, the drive system that I used for this is the same exact drive system that you saw on the very first slide with my first scope. It's a lightweight EQ3 Orion EQ3 tripod. It just has 2 small stepper motors, but if you balance everything, that's enough. And so I got a second set and took the gearbox off of this one and got a matching gear and I had to do the math and figure out how fast I wanted to turn it. But so this is all, there's actually an access port on the other side, but otherwise it's all enclosed. There's no way to get to it. But this is the system that floats through the, for the end of the tangent arm. It accounts for the difference in distance from the top of this to the center and the center of this to the center. It changes slightly, and the angle, of course. And it's a close-up. This is a 1/4-28 screw, and I actually had to, I originally started with the 1/4-20 screw, but when I was at the Winter Star Party at 600 power, I discovered that the drive motor was a stepper motor, and you could see the steps in the stepper motor. And like, that's not good. So I had to redesign it a little bit. So I had to remake this to, so that it would work with a higher motor speed. And since the hand controller is just this basic little, it had a couple of push buttons on it, and that's it. And so how do you change the rate? I didn't know how to program it, but someone pointed out that you can just use change the crystals that are giving out the pulses that tell it, how long is a second. You just speed that up, and it fools it into thinking, well, I need another step sooner. So I ended up 40% faster, and so I had to accommodate that by using a 1/4-28, so it would match the right ascension drive. So that's why that ended up with 28 rather than a 20. And this is the drawing I made. I made very few drawings, but this is one of them. This is to figure out all the dimensions I had to have, the motor here, the gear I bought, Boston gear. Just try buying one little gear with the metric thread, metric teeth and everything. It's like, so yeah, to figure out how all this fits together, you got to figure out the distance, center to center, the size of the holes. I ended up going with the backlash adjustment, bearing directly on the bearing race rather than having a plate here. But this is pretty much, this is just the dimensions of the screw alone. I had to know all the lengths to cut, the exact spans, diameters, everything. But yeah, that's something I had to really plan carefully. So I actually made a drawing. And this is the notes that I took to figure out the drive rates, figuring out the split ring diameter. I used a rollerblade wheel, a urethane rollerblade wheel to drive the, from the shaft of the motor to drive the clutch to move the right ascension drive wheel. So this is all the math I did to figure all that out. So I wanted a compact clutch so that you didn't have to loosen anything or tighten anything, unlock or lock. All you have to do is grab the scope and move it, and when you let go, the drive motor is driving. So you have to have a clutch, and this is very compact. I got this, there used to be what's called the ATM list, amateur telescope making list. It's now pretty much migrated to cloudy nights. But I asked, you know, all right, I want to build a cone clutch. How do you do the math? How do you know how much friction you're going to have? So he sent me this, and I was like, oh, yeah, that's what I need. Perfect, thank you. So yeah, it's a little bit involved, but you know, it's not that complicated a formula right up here. It's pretty straightforward. And you know, I figured out this is all my you know, just trying different iterations, and I ended up with this, and it's like, yep, that'll work. So it goes from the drawing to this drawing. So now I'm actually building it. I have to have a way to assemble this around the wood. One side has the drive wheel, and the other side has the clutch, and then you have the adjustment, the friction adjustment in the back right here. You twist this, and you know, you have a spring that puts tension. It pulls back on this shaft. It bears against this becomes a thrust bearing, and so there's two identical bearings with a spacer. One just rides, and then the other is thrust. And this is the this right here is the outline of the skate wheel, and so it's just riding on this shaft. It's floating, but it's pressed onto this piece, which is where the friction is applied. This is the friction material is from a plastic milk jug. Turns out it's a very low stiction, which, you know, the difference between static friction and dynamic friction is very small. So when you start to move it, it just starts moving. It doesn't jerk. So that's what I use there. And so I needed to figure all the diameters and the lengths, how long it has to be to, you know, it has to fit where, you know, there's a limited space to fit. And I discovered that here's the split ring here. And if you go stainless steel on stainless steel, it's very slippery. But if you drag stainless steel across aluminum, there's some real drag. It grips quite well. So I had to make an aluminum shell to fit over the stainless and press it on. I think press fit there. And you go from the drawing to the actual clutch. Motor drives, there's a drive shaft right here. That keeps going all night. And so the wheel turns all night, but when you want to move the scope, it just forces this to twist, and it twists inside the cone here, and you adjust the tension here. And also there's this knob here adjusts the engagement tension. You can disengage it, so you loosen that, and the shaft drops away. So you can actually, you want to do that before you pack up, so you don't leave a dent in your urethane. And this is just from the other angle, from the outside. That's a rollerblade, yeah. And I got that idea from Stellafane. He had like, I think 3 of them in a gear reduction. It was all wheels, no gears. So there's no backlash. There's no gear backlash. And this is, oh yeah, this tells a story here. Let's see, is it? No, what was that? Yeah, here. When you apply friction here, I mean, you're basically controlling the motion of the declination of the telescope with this friction disc. Again, this is aluminum on a liner of milk, plastic milk jug. So the adjustment is here. There's a knob. You can change the adjustment. It's anchored here. So you have torque being applied when you want to move the telescope, but when you let go, you're only controlling that torque on one side, and you have that torque applied all the way out here, and there's flex. It flexes all the way through the tube to the other side, and so the way you control that is get back here. Okay. I knew that might be an issue, so I was designing that into it, and when I actually tried it out, I'm like, yeah, it does. There's a lot of hysteresis here, so I added this is half the size, 2 inches instead of 4 inches, and you just added just a tiny bit of tension to this side, and it damps it out right away. When you let go, it just boom, and that's it. And this shows the encoder for the digital setting circles. This tells the computer how much you've rotated. Anchors down here. I didn't drill these holes before I welded, so drilling these holes here and for the finder scope here was kind of a challenge. Yeah, I think I had a long flexible drill, and then for the threads, I had to like just take the tap and grip it with vice grips and so when you have an equatorial mount, you need to polar align. Well, you don't have to have the polar scope right on the axle. It can be anywhere as long as it's parallel to the axle. And this is an accessible point where you can get down below it and look through it. And I built this thing with you can actually rotate this now within this Delrin cage. So that you can position the ring in a place where you can see it, then you rotate this for the season. There's a reticle in there with the various stars, and it points to Ursa Major and Cassiopeia the other direction, and you line that up, and you line up the other stars, and when you get it all aligned, then your polar line. But and this is an interesting system where you press the button. There's a mini 12-volt battery in there, and there's a capacitor, and all that does is charge the capacitor, and the capacitor lights up the reticle, but then it drains so that you can't forget. You just hit the button, and you can't leave it on. Yeah, something like that. It's really clever. Yeah, it is. So, like I said before, all the wires are hidden. You got these two wires coming out. One is for the declination motor. The other one is for the declination encoder. And they come out of the ring and they plug into this bulkhead here. Well, it's kind of a two-sided bulkhead. There's connectors here for the digital setting circles and for the hand controller on the back here. But in between, there's a space, and this is where you do all your wiring. So a little hidden compartment there. Okay. And so when I finished in 2005, I took it to Stellafane, and this is the judges looking it over. And me accepting my awards for craftsmanship and mechanical design, 2 different awards. Craftsmanship is implementation, mechanical design is the ideas, I guess. Oops. Oh, yeah, that's the awards framed. and not much good if you can't transport it. And this is how compact it is. You can stack it all, and this is a fairly small car, and it fits into just a small space in the small car, and you still got room for luggage and all kinds of other stuff. And this is driven hard and put away wet, as they say. So this is my favorite picture of it. This is my friend Bernie Kosher took this picture too. He got up early. I was sleeping it off in one of these tents, these little cabin tents there, and you can see it's very cold. It's frosty. This guy's getting up early in the morning, and so I didn't cover it up because it was all covered with frost. Everything just stays wet, so you just leave it. But I like that picture. Like I said, it wasn't done. I still, have to do repairs and that modification to the drive system. The upper cage, used to be plastic. Now it's carbon fiber. The plastic kind of rippled when it was in a car that got too hot for too long, and that was that. So, so I had to come up with something that was not temperature sensitive. And this is just I took these pictures demonstrating the limitations of the split ring, where the ring is at the very end. There's a screw there, there's a stop, and so that keeps the ring from running off. But you can't go any lower and down to the north, and so to go there's a gap between here and over here. I'm sorry, there, where you can't view the actual horizon, at least when it's jacked up to the north a little bit, because you're hitting on the other side. You hit the ring with the truss tubes, and that's the limitation of the split ring. And to minimize that, you want to make the ring as large as you can without it getting in the way, and that's not much you can do. It is what it is. But there is that slight limitation. Now, this is my current shop. Okay. So that's the lathe, and this is a bunch of paints and stuff there. This is a horizontal bandsaw, very handy. You get a 4-inch thick piece of stainless steel. You just set it on there and turn it on and walk away. Yeah, well, it's actually pretty quick. Here's the mill I bought fairly recently, and this bench actually came with the basement. When I moved in, it was already there, and that's he's got motors here that are older, probably older than I am. And I built these shelves recently to give me a place to store my stuff. And here is the table saw somewhere here. Anyway, there's a table saw here. So this is my workspace now. And I think I have to get out of that. Yeah. And so this is another scope that I've looked through many times over the years. My friend Alan Daroff, this was from 20 years ago. He died of COVID a few years ago, and I inherited the scope. And this is a very massive mount. A very clever guy. He made all of this, every little bit. He's got a motorized iris diaphragm on the front. This is a 1-inch f/30 telescope that you can switch. There's a flip mirror here. It's got solenoids and all this stuff, and then the Etalon filter for each alpha is here. Then the other eyepiece, yeah, that's the eyepiece, the main eyepiece. And then he's got an old video camera on here. So there was, I don't know, a few years before he died that it hadn't been used. And so anyway, So yeah, this is a massive mount. This is like a 3-inch solid steel shaft. So you got an idea of how heavy that is. 1-inch thick aluminum plate, another 1-inch thick aluminum plate. This is like a 2-inch steel shaft. He built it. He just accumulated stuff over the years, and the drive motor. There's a planetary drive, so that you can have 2 different motors. The constant one, and then a slewing motor. So you can have 2 motors at the same time, and it runs off of planetary. Both axes have that planetary. Very, very clever. Yeah, this is more close up of the main eyepiece. This is your picture-in-picture. You can have a full disc view through this, or through the main scope. You can switch back and forth. There's a flip mirror there. Everything's powered. Oh, and then also up here is the white light. So you can switch from F30 to F15 and just use a Herschel wedge for white light. So when I inherited it, I'm like, what am I going to do with it? At first I wasn't going to take it. I'm like, no, I can probably think of something. This is a lamppost in my front yard, and I'm like, yeah, okay, this will work. It already has power, so that's good. Well, not really. This is a 4-foot slab of concrete, but turns out it's only a couple inches thick, and it would not have been enough. It's only that thick because underneath that is bedrock. There's barely enough lawn, there's topsoil to make a lawn here. It's very, very thin. So these are the parts of the mount, and nothing worked. I had to get everything. This is his hand controller. It's just a Bakelite frame, and you just put all these switches, and it's just it's incredible. And then it all goes through this junction box. He plugs this in, and then power goes here, and then it feeds back to here, and then the 2 motors plug in up here. And so yeah, I'm rehabbing all the motors, making sure everything works, adjusting the backlash and everything. Yeah. This is the solar filter. You got the this is the energy rejection filter. You can use full aperture, but you don't have to. This is a much smaller piece, and this is like a baby food jar lid that he has just like attached. He just cut the thing out, and for the Etalon, to tilt it, if you can tilt it, you can go off band and look at things that are coming blue shifted at you. You can see material. As you tilt it, you can see the band shifts, and you can see different areas light up or go dark, depending on which way it's moving. And it came in handy. It was surprising. Some people, I know someone that has a filter like this and got rid of the tilter. And I'm like, no. After I saw that, I'm like, I'm not doing that. So this is the back half of it. I'm looking from the front towards the back. This over here is the Barlow that changes it to F30. And it's got a little shroud around it. And this bar here is square, and you can rotate that into the light path, or you could rotate it out. And here's the Herschel wedge from the other focuser here. That's on a shaft. You drop that in and rotate it into place, and you can look at white light when this is out of position. Again, very, very clever guy. This is looking at it from the other direction. You're looking at it from the back towards the front. This is with the Barlow in position for F30, and this is the Herschel wedge out of position right there. This is what it looks like from the outside. This is the focuser. That's the other end of the shaft here. This is where the Barlow pops out. You got to have a little cover for this, but that's how we get it out of the way. This is the whole focuser with the Herschel wedge. And Yeah, is a sardine can that I use to cover the slot. So yeah, I didn't build this, but you know, it was a kind of a project to get it back into working order. And here it is working. And I mounted my PST to the side of it, and you got the white light here. The Herschel wedge is engaged, and here's the light dump, the energy dump, the sunlight coming out the side. And here's the Etalon and the tilter. So this is what it looks like in action. So this is what kind of a side project, but man, it works. It really, it's nice having 6 inches of aperture on the sun. It really is. And this is my next project, my 26-inch Cassegrain. This is what a 26-inch blank looks like. It's a slab of 100 pounds of borosilicate glass. And I left the shop vac in here in the picture for scale. Gives you an idea of how big it is. It's a monster. I hope I haven't bitten off more than I can chew. So this is Oslo software that you can design anything you want as long as it has 10 surfaces or less for free. And so it shows the performance on axis is pretty good. This is the center, and this is at the edge of a camera, a full frame camera. It's not quite within the airy disc, but you would probably not even see that in most cameras. You'd have to have really small pixels to notice that that's not a dot. So it should perform, if everything goes well, pretty well. This is the layout. This is 26 inches. This is like 1.2 meters, so it's going to be a very short telescope. And then the tertiary points the light out the side. The reason there's an angle is so that you're never looking straight into it. You're always looking at a downward angle, even if it's pointed straight up. And this will be cranked, rotated slightly up, so that even if it's horizontal, you're still looking down into the eyepiece. You're never looking straight in. I find that uncomfortable. But the angle doesn't matter. You can change the angle, doesn't change anything else. And for the 26-inch scope, you need an 8-inch finder. At least I do. So this is an old paracord modified to fit a JMI focuser. It's a pretty cheap standard Crayford focuser, and the carbon fiber tube was not cheap. It was like, I don't know, $800 or something. This is I've had this mirror cell in here before to demonstrate. It's a kind of a proof of concept, because I have to have, for the secondary of the Cassegrain, I have to have a cell that does not move the center of the mirror when you adjust the tilt. And so it looks pretty ordinary from here, but when you turn it over, you see the screws are canted. They are tangent to the sphere with the center of the mirror at its center. So everything you adjust is around that center. And at the center of the cell, it bears on this. This is a spherical washer set. So that's how that slides back and forth. You know, one slides on the other, but the center of that sphere is where the center of the mirror is. So the mirror doesn't move at all except in tilt. And this is using my new milling machine to its full advantage. I got this tilting what's it called? Anyway. Yeah, it's a rotary head. Thank you. And here I'm doing a little delicate machining, clamping this little piece and cutting it with this monster cutter. But you rotate the rotary head around the center, the center of the mirror, so you get the right radius of the mirror clip. This is one of the mirror clips on this cell. So it's fun with the milling machine. Now this is the other thing that comes in handy. It helps coarse grind the glass. You can use, this is a diamond hole saw, and you turn that very slowly, and you turn the mirror under it, and it becomes concave when the table is tilted slightly. And then you move to the other side, and it makes, you grind over the edge, and it makes that one convex. So you can get very close to both curvatures, and it doesn't take you a week of grinding by hand. It just takes a couple hours on the milling machine. And this is a new design for the secondary of the finder scope. This adjustment tilts the mirror very close to its center on here. So when you adjust it, it doesn't translate its position as much as if you tilt it from way back here. That moves the position of the mirror pretty far. So this isolates it to very slight motion, and this adjuster rotates it so you can tilt in the other direction. And this is what it looks like when you actually have the installed. These are 4,000th thick stainless steel shims. So you get almost no diffraction from the spider, at least directly on axis. This is a close-up of the adjustment. You turn the screw, bears on this, and it turns the shaft that the mirror is attached to. And again, still very, very thin, even close up. And this is how you adjust it. This is a guitar tuner, and this is it just clamps, wraps around here and clamps into here. The screw go right through the shim, and you wrap it up, and you just turn a screwdriver on this end, and you can get hundreds of pounds of tension on there. And very, very rigid. This is what it looks like when you look through it. You can almost not see the three shims here. That's the point, so that you minimize the diffraction spikes. That's what it looks like installed. And this is all put together except for the back end. So what it looks like from the outside. And what's that? Oh, just the 8-inch. Yeah, if I have a way to mount it, yeah. So this is my my scope in Texas. This is another favorite picture. This is actually a selfie. Just set the thing on a tripod and set the timer, walk over there, beep, 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 and 1 minute exposure, hold still. And I like this picture. But anyway, thank you very much. That's my presentation. Any questions?
On your beer keg scope, you got a big metal frame there. Do you get any thermal effects as as outside temperature gets colder, do things
Yeah.
bind or change?
Not that I know of. I mean, it's hard to isolate that from just poor seeing. It's hard to know if it's the air above the scope or right around the scope. I certainly have noticed, when the mirror is warm, you can see that. But it's 1.4, 1.3 inches thick. It cools off in a couple hours. Generally after that, no, I haven't really had an issue. Yeah, like I said, I put insulation directly, between the steel and the light path at the bottom to try and minimize any kind of, if it's cooling too fast or too slow or whatever, it should be isolated.
What
So
about with the mechanics, the actual, like, I think he was asking more about like the actual framework. Is it shrinking in size, or maybe not not quite sliding as well because of the changes?
Oh, okay. Well, like I said, I had the issue with the as the ring walks in and out of the across the rollers, you do get a little added friction, and it can drag it can put added pressure on the clutch, so it gets tighter to move or looser depending on which direction you're moving, what part of the sky you're in. So I've had that. You just kick the clutch a little and settles it right out. But yeah, it works pretty well. It's not perfect, but it's given me 20 years of enjoyment. So
Scott, question for you. How many hours have you put into making that?
altogether, it took 4.5 years. Probably two and a half to make the mirror, and and I started building the rest of it while I was making the mirror. So I don't know, thousands probably. And a lot of that time is just sitting there. All right, how am I going to do this? Just looking at it, figuring out what's next. And I did you saw the couple of drawings I had and the figuring I did. There was not a whole lot of other drawings that I didn't really have anything else. There's a lot of just staring at it and thinking, all right, how am I going to do this? What do I need to do? Yeah, it was, it was very rewarding. I think, it was worth it.
Your 26-inch Cassegrain, you said the glass is 100 pounds.
Yeah.
How did you get support, like the thinness of those veins? What material did you use, and how did you get, that kind of weight supported with such thin veins?
The veins of the spider.
Yeah, that's for the
That's on
8-inch.
Oh, that's on the
8-inch.
secondary.
Oh, that's the
On the side,
second.
that's the 8-inch.
Oh,
Yeah,
so
that's-
so the one is in the base.
Yeah. So
Okay.
that's
How heavy is the
and
secondary mirror?
the secondary for the 8-inch or the Cassegrain.
The Cassegrain.
That's an 8-inch mirror. So it's just a few pounds. It's going to be a carbon fiber cell. But they're going to be 3-inch veins on that versus 2-inch wide veins that I have for the 8-inch. Because there's a much wider span. Of course, you got to, span 13 inches across. But anyway, yeah, it's I'm not really worried about the weight. It's more about rigidity. In other words, how much, how fast does the vibration damp out? I actually put a piece of memory foam right behind the secondary of the 8-inch, so that when you ping it, you clang it. It has something there to damp out. Yeah. Memory foam, yeah.
All right. Anything further?
So I'll get a bigger piece of memory foam for the 8-inch.
Any
in a
questions on
second there.
the Zoom session? People left on the Zoom session? Okay. All right. Oh, thank you.
All right.
Very good.
Thank you.
Outstanding.